Now that we have defined what a definite integral is and how it can allow us to compute the area at least in one case, and now that we have established the fundamental theorem of calculus that allows us actually to compute those definite integrals in a quick way, we're going to fly through many applications. Going to fly for a couple of reasons. Number one is because the fundamental theorem is going to allow us to actually compute and obtain formula for those applications very easily. The other one is because they're fairly easy applications, so it's going to be very easy to follow them. So the first one is to figure out how we can generalize the whole idea behind definite integrals to totally solve the area problem. And this is something that is traditionally called areas between curves. Okay? So the idea is the following. So far we've used definite integrals to compute the area of a region that looks like this. So it has the bottom straight edge along the x-axis, two side edges vertical to the x-axis, and one top edge which is not straight, but it follows some kind of a function f of x. Almost a rectangle except for the top edge. And we have seen in this case the area is given by the integral from a to b of f of x dx and can be computed as long as we know how to take the antiderivative of f of x through the fundamental theorem of calculus. Alright, what if we're dealing with a region that is curved all over, something that looks like this? Now, by the way, this curve is actually symmetric top and bottom simply because I'm not very good at drawing these curves, but it doesn't have to be. I'm just thinking of any region that has a curve whose boundary is made up of curves all over the place. So how can we do that? It turns out that the general case can actually be reduced to a very special case, namely the situation where the region is bounded by a function on top and one on the bottom. So a function that looks like this. And that is because if we have a more complicated function or a more complicated region, what we can do is we can cut it up into smaller pieces so that each of those pieces has one top boundary and one bottom boundary. And we can cut it up in as many pieces as we want. So we're going to analyze just the top case because that's the only one that is worth looking at. Alright, well, I'm going to show you two arguments for how to set up the area of a region which is bounded by two curves, one on top and one on the bottom. The first one is a simple geometric argument. We're looking for the area of a region that looks like that. It's bounded on top by some function f of x and on the bottom by another one. Well, I can think of this region as being the difference between two regions, one that looks like this and one that looks like this. Can you see how the original region is the difference between these two? But also, can you see how both of these regions now are exactly of the type that we've used to define a definite integral? Which means that the area we're looking for can be written as the integral from a to b of the top region f of x minus the integral from a to b of the bottom function g of x. Now, because of the properties of definite integrals and in terms of limits of sums, or if you want, because of the properties of antiderivatives, this is the same as writing the whole area as the integral from a to b of the difference between f of x and g of x in dx. And so this is the simple formula that we're going to need to figure out what is the area of a region bounded by two curves. Now notice a very important fact. In this formula it is essential that the first function f of x be the function which is on top and that the bottom function be the second one. Now if those two functions end up crisscrossing each other, then we'll have to break up our integral into smaller pieces just like I mentioned earlier, because for each of those pieces we have to make sure that the top function is used first and the bottom function is used second. If we mix them up, we're going to come up with some really incorrect conclusions. But there is another way that I can show you why where this formula comes from, and it is one that comes directly from the definition of definite integral, and it also gives us the first glimpse into how to use the definite integral in applications which are something other than its originally intended application. I will call this the four-step argument. Okay, remember the four steps for constructing an integral? So we have our region and we want to compute the area of this region. So first thing we're going to do is we're going to slice that region. We're going to slice it into several pieces. And then what we're going to do is we're going to say, all right, each one of those strips is really approximately a rectangle. So we're going to approximate the area of each of those strips. So of course, each of those strips is going to have a width given by delta x as usual. And the height, if you notice, is simply going to be the difference between the top and the bottom functions. So it's going to be f of xi minus g of xi for each of the slices. The third step was add up. So we're going to simply add up all of these products for all of the n strips that we have computed. And then of course the key calculus step is that of taking the limit, which allows us to then obtain the exact area of this region. And of course, once we do this, what we end up with is, remember, the limit as x approaches as n approaches infinity of the sum from 1 to n, that's exactly going to be giving us the integral, and the delta x is going to give us the dx, the differential. And therefore, this whole expression will actually become the integral from a to b of the difference between f of x and g of x in dx. So again, this is exactly the same formula as before, only obtained through a different method. But again, it's quite important for you to realize that it is this second method, this four-step argument, that we will be using for the rest of the applications for which we will use integrals.